the introduction. Happy to be here. Yeah, this talk is, I'll talk about some mathematical work, but it's motivated from a couple of different directions. One is from some problems in physics relating to capillary droplets on rough surfaces. Another is coming from some type of abelian sandpile model. And it turns out that somehow in both of these situations, you end up seeing a kind of similar picture, and there's turned out to be a kind of similar mathematical explanation. So I'll give some pictures, and then I'll talk about some math. Okay, so let me describe these pictures a bit. So this is from some things related to capillary droplets. The picture on the left is a picture of a solid surface which has been fabricated by engineers. This picture is at the 1 micrometer scale. So what they've done is they call this a micropillared surface. They've fabricated the surface with these little circular pillars arrayed on a square lattice on the surface. Again, everything here is at the micrometer scale. And a group of physicists was interested in whether you can. Well, a lot of people have been interested in whether you can design surfaces to have particularly nice wetting properties. There's things like self-cleaning surfaces where the water droplets just roll off, and there's other kinds of applications as well. So they were interested in here's this fabricated surface. What are the wetting properties? So they put a water droplet on the surface. So this is a top-down image of a water droplet that's sitting on this surface. It's at the 1 millimeter scale, so it's 1,000 times the length scale of the microstructure. So at this length scale, the surface, although it does have these micropillars, it actually looks pretty smooth. I mean, it's like looking at a surface of a table, in our life. It looks pretty smooth to us, but if you zoom in, you start to see some microstructure. And what you might expect, as is sort of the mathematical idealization of a smooth surface, and you ask, like, what is the shape of a capillary droplet on that surface, it would be a spherical cap. It has some axial symmetry. It looks nice. But that's not what happens here. So generically, you put down a water droplet, and it has these things that I call facets. So there are these flat parts in the contact line. So just some terminology. The contact set is the region of the solid that's touched by the liquid. The contact line is the boundary of the contact set. It's the triple phase interface between water, air, and solid. The contact line aligns with the lattice directions of the microstructure. Okay? So that's kind of interesting. And we'd like to have a PDE that describes this. So we can derive a PDE that comes from the microstructure and tells us that the macrostructure has these features. So let me, yeah. I think they're orthogonal. What's the question?
The scale looks different.
Yeah, I believe it's a square lattice. The picture is just taken at a certain angle. Yeah. Okay, so just to say something very brief about what the sort of classical PDE you would write down for the shape of a capillary droplet on a surface is. So I have my solid here, my liquid region here, and here's air. So the free surface here is going to minimizing a perimeter-based functional. But typically, the natural thing is to put a volume constraint. So what you end up with is a surface of constant mean curvature. Okay? And so that's sort of part of the PDE that describes what the liquid droplet looks like. But there's another part of the sort of Euler-Lagrange equation that comes from the energy minimization principle, which is that this is along the contact line, along this triple phase interface. And it says that the angle here is specified by the parameters of the problem. I didn't write down what all the parameters are, but it's fixed by sort of the chemical properties of the surface and the liquid that you're using and the vapor that you have. In this case, I said air, but whatever. So that's the classical picture. The idea for us is to say, okay, well, we have this equation, and this equation is correct at the microscale. It's correct all the way down at this scale and even further, right? When you zoom all the way in, imagine this as a graph of a function, it starts to look smooth when you get way smaller scale. And at that scale, we're saying that this is the correct thing. But we want to know what's happening at a big scale, okay? So we need to find some kind of effective large-scale equation. It's a sort of a typical problem of homogenization. I'm sorry that maybe this isn't visible over in the corner. Okay, so that's one sort of problem. so here are some pictures that are coming from a different origin. These pictures are coming from something called the boundary sandpile model. I'll write something about that over here. Try to describe it very briefly. So basically, it's an evolution of subsets of the lattice. So I'm just going to write down something very specific. I'll have the ball of radius n around 0. And I'm going to have a function uk, which is going to be equal to n on this set. And I'm going to have some set sk. And as I said, the k there is some like time evolution. I'm evolving subsets of the lattice. And so my function uk in the set sk, it's going to be a discrete harmonic function. And then it's going to be equal to 0 in the complement of sk. And then how do I evolve? Well, S0 is just going to be this Bn, and the ball of radius n around 0 in the lattice. And then sk plus 1 is just formed from sk plus all of the points in the boundary of sk. This is a discrete subset of the lattice. So by boundary here, I mean the outer boundary, the outer site boundary. So points that have a neighbor inside, such that the Laplacian of uk is strictly larger than 1. And this is going to stabilize. So after a finite number of steps, it stabilizes to something. So, and what it stabilizes to is the minimal solution of the following problem. So Laplacian u equals 0. This is, again, discrete Laplacian in its positivity set minus the Bn. U is equal to n on Bn. And the Laplacian of u is less than or equal to 1 on the boundary of the positivity set. Right? If it wasn't less than or equal to 1, then I could keep expanding. Right? And so my claim is that the stabilization is the minimal solution of this.
Sorry, how do you update u?
How do I update u? Because I resolve the PDE that I wrote here. Yeah. So at each step, I get a new set. Then I resolve the PDE. Then yeah. OK. So so why is this a bit like the problem I wrote before? Well, somehow. What?
What's that in brackets in minimum?
This is the minimal solution of this problem.
And what do you mean by that?
There's a lot of solutions, and I just take if I take a minimum of any pair of them, it also satisfies. OK, the pointwise minimum of them is a super solution of the Laplace equation, and so if I resolve the Laplace equation in the new domain, it actually satisfies this. There's a comparison principle for this problem. And so, so the minimal solution of this problem is the stabilization. I mean, it's not so hard to figure out because there's a comparison principle. Any solution of this will block the evolution. You can't get past this because your Laplacian will be less than 1 everywhere. And the minimal thing, and if you stopped before this, then your Laplacian on the boundary would be bigger than 1 somewhere. So this actually is a little bit like the previous problem. I mean, you should think of this as like a slope condition. It's saying that as long as this kind of contact angle is too large, you move out, and the contact angle decreases until it reaches the equilibrium value. So it actually looks a bit like that problem in a certain way. And when you take the scaling limit as n goes to infinity, you rescale, you see shapes like this. And you might think that you'd get a ball when you do this. I mean, everything looks rather symmetric, but you don't. You remember the lattice structure just like we saw in the previous slide. So this is a picture in 2D of the positivity set of U, and this is a picture in 3D of the boundary of the positivity set. It has these, you see these facets. I mean, these are numerical computations. You see these facets. You see what look like maybe some higher codimension facets in the boundary as well. And that's something that we wanted to explain from just a totally different perspective than the first problem. OK, so I'm trying to go to the next slide, but OK, there we go. So, so my claim is that somehow both of these are described by a similar sort of problem. Now, the first problem obviously is a physical problem, so I need to model it. I first chose this as my model. I'm going to make some vast simplifications, but I claim that there'll still be some interesting qualitative features that remain. So instead of taking a perimeter functional and getting a mean curvature, I'm going to linearize that, get a Dirichlet functional, and get a Laplacian. So it's easier. I'm going to assume that my liquid drop is the region under a graph of a function. That's my function u. Okay? And I'm going to remove the volume constraint and instead sort of imagine that I can sort of look near the boundary and think of imposing Dirichlet data and resolving. I'm getting a little overly complicated, but my point is to say I'm making a bunch of simplifications there and then saying that, OK, this is the right problem to describe the scaling limit of both of these problems. OK? So this is it looks a bit like a classical free boundary problem. So we have my function u is harmonic in the set where it's positive. And on the boundary of the set where it's positive, okay, so classically a free boundary problem, you impose that the Bernoulli free boundary problem, you impose that the slope is equal to 1, okay? And the reason this is a free boundary is because you're basically solving a Dirichlet problem and a Neumann problem. So you can't just do that in any domain. It means the domain is basically part of the equation, okay? In this case, I have something that's not an equation. It's more like a differential inclusion, okay? But that's a real thing. That reflects the sort of that reflects exactly the non-uniqueness that you get in this epsilon problem. Okay, when you have this rough surface, you get a lot of local energy minimizers. And my claim is that a problem of this form describes, in the scaling limit as the microstructure goes to 0, describes what the large-scale shapes look like. And if you want to think back to this, right, you place the slope by a contact angle, and you say the contact angle is in a certain range. Okay.
What is the meaning of these brackets I'm seeing?
So yeah, so I'm saying that I'm looking for a domain that has a harmonic function in it. Typically, I'll also put a Dirichlet boundary condition. And on the boundary of this domain, the positivity set of U, the slope has to lie in a certain interval. And the interval is allowed to depend on the normal direction to the boundary. Okay? So what this means somehow is that you go back to this picture and you think of, is it possible to find a plane-like solution of this microstructured problem with a given contact angle, right? At the tiny microscale, it satisfies the classical condition that cosine theta is fixed, right? But then it wiggles, and at large scales, it has a large scale slope. And that large scale slope does not necessarily have to agree with anything. It just lies in some interval that you need to compute, okay? So that's what this means. And so my claim is that the facets that we see in these pictures are caused by discontinuities in the endpoints of this pinning interval. Okay? So it really has to do with the qualitative properties of how this pinning interval depends on the normal direction. And okay, so that idea that discontinuities in the slope on the boundary cause facets goes back a ways. But what we've been doing recently is we actually derived this problem in the scaling limit of the boundary sandpile model and in the homogenization limit for this free boundary problem. Keeping an eye on the time. This is a free boundary problem now where I do specify the slope. And this Q is sort of modeling the roughness of the surface. It's periodic, which sort of fits with the pictures that I showed before. And it's varying at some epsilon scale. So that's a microscale compared to the scale that I'm looking at. Okay, so I'll show a few more pictures. So this is a picture of the pinning interval that comes from the boundary sandpile model. You can compute that numerically. And you see that it has discontinuities actually at every rational direction. That's what it looks like. And at irrational directions, there's some radial symmetry that's recovered. This is a picture of a grayscale map of the upper end point of the pinning interval over the sphere in 3D. And now actually there's discontinuities along every rational hyperplane of each kind of dimension, right? Dimension 0 and 1. Okay, so we had these numerical computations, which look very nice, and we wanted to explain them. And so we were kind of amazingly able to derive an exact formula for that boundary pile model, which I'm short on time, so I don't want to explain all the details of the formula. But it's basically just the exponential of the sum of some Fourier coefficients of a very specific function over all the rational relations satisfied by the vector E. And so you kind of will just see from this all the rational, irrational structure of the pinning interval. And of course, something like that's not going to be possible for this continuum model with the function Q. But still, this was some inspiration to say that, OK, this is the right sort of continuity-discontinuity structure. And so I was able to prove in 2D that the pinning interval coming from this continuum problem is continuous at irrational directions and may have jump discontinuities at rational directions. There are examples where it has jump discontinuities at rational directions. I believe it's a generic phenomenon, but I don't know how to prove that. And I think I'm running a bit low on time.
S is basically the discrete Laplacian. What's that sum of?
Where is is a log of it? Yeah.
Did you consider non-square lattice?
I have not done that yet, no. And I mean, I've sort of transitioned from doing this to trying to study this continuum problem where you don't know as much about what these sort of sloped solutions are, and so they run into other difficulties there. But I think, yeah, I know I haven't studied it. I think it would be interesting. And OK, so I mean, I know I have to finish up, but just to say briefly, it turns out the original thing I wrote down, that differential occlusion, looks a little bad because it's not an equation. It turns out that somehow the minimal and maximal solutions play a key role, and then you actually have an equation. So like a minimal solution would be when the slope, it always takes the maximum allowed value. The difficulty comes in is that this assignment is discontinuous in the normal direction, so there is no theory to deal with that. I mean, it's exactly what causes the facets. It's the interesting part, but we needed to develop some new well-posedness theory, which we can do in 2D and in higher dimensions under some convexity hypothesis. And the difficulty there has to do with all these different kinds of codimension discontinuities that we don't know how to deal with. So I know I've run out of time, but OK, I don't know. This is, to me, I think it's a new kind of free boundary problem that, I mean, you can always just write down something random, but we've derived it from some scaling limit of physical problems. So I think there's a lot of open questions that are interesting to ask about this. I think that one of the things that really needs to be done is to put back in the volume constraint. It's surprisingly difficult to deal with it. It becomes more like a system than this problem where maximum principle is really useful. And I'll stop there. I'll leave up my open questions.